Seems just a few years ago that I was also an undergraduate like you, and at that time I didn't have any idea what research was all about. So I mean, this is an opportunity for you to find out what kinds of things people work on and what people really mean when they say research in computer science. And I hope you will consider all doing graduate school in computer science. So first of all, I want to ask, how many of you have taken a class in graph theory? Okay. How about in algorithms? Most of you. How about in linear algebra? Okay. So I'll try to assume not too much about linear algebra, but I want to make this talk very interactive. Okay. So if you have any questions of any sort, you don't follow anything, just raise your hand and ask, and I'll answer. So the title of this talk is about a particular way to look at graphs through the lens of linear algebra. Okay. So it looks a bit foreign, and I'll try to explain what the motivation is, and we'll use that way of looking at graphs to understand how to partition graphs. Okay. So first let me understand why, I mean, where do graphs come up in practice and why you would need to partition graphs. So here is one example. So this figure describes a biological system. Okay. So each of these circles here, each of these nodes is a gene, okay, or maybe a protein. So these are outputs of some biological process, and the connections are regulatory connections. So for example, this gene is turned on if the certain genes which are its neighbors are turned on or off. Okay. So whether the gene is turned on or off depends on the status of some other genes. Okay. So this is some huge network which you can realize as this graph. So a graph is basically a collection of nodes, and you have edges connecting pairs of nodes. And one interesting question that biologists ask if you present them such a graph is whether you can partition the graph into separate clusters, so that this group of gene acts to do some particular thing, this group of gene acts to do some particular thing. There may be some connections between those particular groups, but the connections are fewer than the connections within the group. Okay. So each group acts together in some way, and then maybe two groups act in concert with each other, but they are more or less independent. Okay. So the question is, how is it possible just by looking at the graph to divide the graph into clusters? So just by looking at it, you don't know. I mean, so this is some arbitrary way to draw the graph. It could be that this gene is very linked to this gene. Okay. So it's not apparent just from looking at the graph, but maybe we can run some algorithms on this graph which can tell us which are the genes which are acting together as a group. Okay. Another example is this one. So you have, so suppose you are a terrorist and you have or some malicious person, and you see this network. Okay. So this is the network of undersea cables which provide internet access to all of the world. So for example, you see that Africa is very sparsely linked, whereas this connection between North America and Europe is very thick. Okay. So if you want to say disrupt a connection between, say, the Philippines and South Africa, you would only have to connect some small number of cables which go from here to here. Okay. So one question you could ask is, what is the smallest number of connections that you would need to break in order to isolate a certain part of the world? Another question, this is maybe not so much of a algorithmic question. So this is a network of who is suing who in the mobile business. Okay. So this is taken from October in 2010. So you see that there are even some cycles in the graph. Qualcomm and Nokia are both suing each other. So I mean, when presented such a graph, I mean, one possible type of question you could ask is, if it's, I mean, there may be groups of companies who are acting together, okay, who are acting together to protect their interests, and they are suing other companies who don't have their interests. Maybe, I mean, it's not true in this graph, but there are situations where you have a huge number of agents, and you have groups of people who are acting, who are colluding secretly, and then they have, and there are other groups who are colluding secretly, but just from looking at the graph, it's not clear who is communicating with who and who are the groups who are working together. Okay, so one example which so one of the speakers, Dinesh Garg from IBM, I think he may mention is you have suppose you have a financial network, okay, and you have knowledge about who is who is transacting with whom, so who is paying to whom, okay, and there are certain groups of people who are scammers, okay, and so somehow they make sure that all the currency passes through them, okay, and you would like to find out such scammers from looking at this transaction network. So all right, and the last example, so this is basically a standard example. So this is a social network. So suppose you have Facebook or Twitter or things like that, and the question is, can you find communities within the social network? So again, you have this situation that you have groups of people who are more linked to each other than other groups of people. So for example, a very big community could be all college students, okay, so they are more linked to each other than say people who are above 60, okay. So and generally want to find thicker communities, so maybe students from some particular college are a much more thickly connected community than people from some other college. So again, suppose you have this this anonymized network where you don't know the names of the people and what information is coming from, and you just know these connections. Can you find communities within this network? Okay. So this is a very hot topic of research right now. So it's a question, how do you exactly define communities? And so you can define communities in some formal way and run algorithms and then compare whether the output of that algorithm really corresponds to what you would naturally call communities, like students from some particular college. Okay, so we'll give a way to define communities in this talk and tell you how you can recover those communities with the algorithms that I'll talk about. Okay. So more generally, actually, you can talk about similarity graphs. So you have nodes in a graph, and then you have edges, and the edges are weighted by some real number, some positive number, which tells you how similar those two nodes are. Okay. And so you think of this as a weight on the edge, and the goal is again to find groups or cuts in this graph. So find a partition of the graph into say two parts, such that the weight of the edges going from one group to the other group is not too large. Okay. So you want to minimize the weight of the cut. Okay. So this is the sum of the weights of all the edges going from one part of the graph to the other part of the graph. So let me make this precise. So this is called the two-way partitioning problem. So you want to cut the graph into two parts. This is part 1, this is part 2, with the property that there is weak connectivity between the two parts, and also each side of the cut should be moderately large. So you don't want that there is only one vertex here and the rest of the vertices here, because naturally there will be a very small number of edges, just the number of edges connected to that node, right? So that is sort of a trivial cut, but we want to get two moderately big chunks. So we want to cut the graph into two moderately big chunks so that the total number of edges, or if the edges are weighted, the total weight of the edges is small. Okay. Generally you have the multi-way partitioning problem. So here again you want to cut, say this is the 4-way partitioning problem. You want to cut the graph into 4 pieces so that the connectivity between the parts is small, and then each component of the partition is not too large. Also equivalently each component, no component is too small. Okay. So the clustering problem is somewhat different. So I'll distinguish between partitioning and clustering. Partitioning is just making sure that the weight across the edges, weight of the edges across the cuts are small, and the clustering problem also ensures that there is strong connectivity inside each component. Okay. So you really want to cut into pieces which are densely connected, which was sort of our motivation, for example, in community detection. The partitioning problem is easier because you don't care about the clustering inside, you just care about what's going on between the parts. So I will describe algorithms for that first, and then we will talk about algorithms for clustering. Okay. So let's see how we can formally define this notion of weak connectivity. Okay. So let's see. So this is called the conductance of the cut. Okay. So suppose we have cut into two pieces, A and B. So the conductance of the cut is defined as the number of crossing edges. So here I am assuming that the edges don't have weight for simplicity, but if the edges had weight, you would basically say weight of the crossing edges. But let's say for simplicity, you can read up later on if you are interested how to extend all of this to weighted graphs, but let's say that we have unweighted graphs. You are just trying to minimize the number of edges crossing the cut. Okay. So I'll optimize this quantity. So the number of edges crossing the cut divided by the minimum of volume of A and volume of B, where volume of A is the sum of the degrees of nodes in that set. So volume of A is the sum of the degrees of nodes in A. Okay. So for simplicity, so just to explain this, suppose that so degree is the number of edges which are incident to a node. Okay. So for simplicity, let's say that each node has the same number of edges incident to it. So this volume of S is just, so let's say that each node has D edges incident to it. So volume of S is just D times the size of S. Okay. So it's the sum of the degrees. So each node has the same degree. So D times the size of S. So this is just number of crossing edges divided by D times size of A, by minimum of D of size of A and D of size of B. So it is, so if A is smaller, so then this is just number of crossing edges divided by D times size of A. So what this means, so the reason I am doing this minimum is because I don't want it to be the case that one side of the cut is very small. Okay. So if one side of the cut is very small, because I am dividing by it, it will mean that this conductance will become very large. Okay. So clearly one of them will be less than, so the size of at least one of them will be less than n by 2, okay, where n is the number of nodes. Okay. So I mean, none of them can be, so the optimal would be volume of A and volume of B are the same. Okay. So this is corresponding to roughly you are dividing into two equal sized pieces. Okay. So you divide by the minimum so as to make sure that you are not doing this trivial situation where you have one side which is very small and other side which is very large. Okay. So our goal will be to find a cut which makes this conductance as small as possible. So you want to both minimize the number of crossing edges as well as make sure that the smaller side of A and B is large. Okay. So this is conductance. So also we wanted, for the clustering problem, we wanted to say that each group, each cluster by itself is well connected. So what does that mean? So one way we can define this is that we can, so we want to say that the internal conductance of A is large. Okay. Okay. So what is the internal conductance? So it's the minimum over all subsets of the conductance between S and A minus S. So if I say that this cluster A, this group of nodes A has high internal conductance, it means that if you look at any subset S of it, there is a lot of edges going between S and the rest of A. Okay. So I already defined conductance, so it was defined as this number of edges divided by minimum of S and A minus S, but I want to make sure that you don't have any subset inside A such that there is a small number of edges between that subset and the rest of it. Okay. So that is the definition of internal conductance. So in the clustering problem, we want to find partition so that the conductance between each of these cuts is small, conductance of each of these cuts is small, and the internal conductance of each of these group of nodes is large. Make sense? Okay. Okay. So, okay, good. So this is our problem then. So we are given a graph and we want to, so in the, let's say for simplicity, the two-way partitioning problem. So here you are given a graph and you just want to find a cut which minimizes the conductance of the cut. Okay, so this is the optimization problem. Unfortunately, there is some sad news. So if you can, so if there is a very efficient algorithm, so formally this means if you have a polynomial time algorithm, so an algorithm which runs polynomial in the size of the graph time. So if you have an efficient algorithm for finding the optimal two-way partition on very large graphs, then it would imply very strange things, like I would become the Pope. Okay, right? So I mean, it implies absurd things, things which we don't believe can happen. So these are called NP hard problems. So problems which are unexpectedly, I mean, which you can solve them, it would be a very unexpected occurrence. Okay, but on the other hand, I don't want to be the Pope. Okay? So I don't want to necessarily always find the optimal two-way partition. Maybe I am satisfied with finding not the optimal partition but an approximation of the optimal partition. So suppose there is a cut which actually achieves, I mean, which makes the conductance say less than 0.01. If I find a conductance which is less than 0.05, I am also happy. Okay, so right. So the message of this slide is that you can't really hope to find optimal two-way partitions unless you can solve very hard problems for which we don't have any idea about how to solve, even after say 50 years of research. But there is hope for finding approximations of the solving approximations of these questions. Okay, so right. So we'll relax this optimality condition. So one very good idea when you are faced with any problem in life is to start walking. Okay, so it makes many things easier. You get your blood flow going and you think of many things. So let's start walking on this graph. Okay, so what does it mean? So let's start from, so here is an idea for an algorithm. So we'll start from any single node in the graph and we'll start taking a random walk in this graph. So remember that when you are taking the walk, you don't know these partitions. Okay, the goal is to find the partitions. But what we'll do is we'll start walking from the graph, starting from some arbitrary node, okay, and we'll see what happens. Okay, so just think about it. If you knew the partition, one thing that you would predict is that if this was really a clustering, you would stay, or maybe even if it's not a clustering, you would stay within, I mean, you would cross this cut very infrequently, right? Because the number of edges, so think of it as a small bridge between islands. Okay, so you would find the way to your bridge very occasionally if you are taking a random walk. Most of the time you would stay inside your own cluster, and then occasionally you would take a bridge and you would go to another of the clusters. Okay, yeah. Yeah, so this is a random walk, which means that at each node you look at all the edges which are incident to you and take one of them with equal probability. Okay, right. So the point is that I mean, intuitively what you could do is you would start taking a random walk and then see which of the nodes you visit most. Okay, maybe you take a few random walks and you would see which of the nodes you visit most, and then you declare those to be the nodes which are in your cluster, and then maybe you would separate that, you would peel that away from the rest of the graph and you would continue. You would start from another node and do several random walks starting from that node, see which of the nodes you visit most, and again declare that to be part of your cluster. Okay, so this is one idea, and it's indeed a good idea, but it's hard to analyze it. Okay, but there are some informal things. So if so you can prove this, and we'll show basically how to go about it. But basically, if a non-bipartite component has high internal conductance, then what happens is that the random walk mixes the component quickly. So what mixes means is that if you start from a node, after a small number of steps, you have almost, I mean, you cannot predict where you started from. Okay, so I mean, you lose information about where you started from, because no matter where you started, you would have equal probability of landing at that node. Okay, so you sort of mix within the component very quickly if the internal conductance is high. And also, as we said, if there is a cut with small conductance, then the random walk takes longer to mix well, meaning that in other words, so I mean, so in the extreme case, right, so suppose this has zero conductance, meaning that there is no edge going from one side to the other. Okay, so what would happen is that basically the random walk would always stay within the same component. So it wouldn't mix, in the sense that you would have some knowledge about where you started from. In particular, you would know that you started from this group of nodes. So basically, I mean, you have these two things. So random walks are good because they tell you whether they can distinguish between high internal conductance and low conductance. But still, it doesn't really give us an algorithm. So we don't. So it's. I mean, so intuitively it makes sense, but it's hard to actually formally analyze this process. Okay? So when you start from a node, what happens when you. I mean, how you actually analyze this process of taking the nodes which are most frequently visited. And anyway, I mean, you can do it, but it's not very clean. So I'll talk about another way to analyze, a different way to analyze this algorithm itself, but viewed in a completely different way. Okay? So this is called the spectral approach. So the spectral approach is the following. So instead of thinking of you acting on the data, like you taking a random walk of the graph, you think of the data itself as an operator and it acts on you. So what it means here is that earlier we were thinking of you are a random walker and you are acting on this graph G. Okay? But now the way we will think about it, so the spectral approach shows that these two ways of looking at the world are equivalent. So what the spectral approach thinks about it is the graph itself is an operator. Okay? So we will describe the graph itself as an operator, and it acts on vectors. Okay? So this vector essentially corresponds to the probability distribution of on the nodes. So which node you are likely to be after a certain number of steps of taking the random walk. Okay? I will describe this more formally, but the way, there is a mathematical way to convert this process of a random walk on a graph to this more sort of understandable process of a graph acting on vectors. Okay? So what is this operator G? So the graph, so this operator G is called the Laplacian of a graph. Okay? And so from now on, the way we will think of the graph is as this operator called Laplacian. Okay? So the graph acts in the following way. So assume again this graph is D-regular for simplicity. So again all of this theory can be extended to the case when each of the nodes have different degrees. Okay? But D-regular means that each node has D number of edges coming out of it. So the graph operates in the following way. It takes in a vector, okay, x1 through xn, which has unit norm, meaning that the length of this vector. So square root of x1 square plus x2 square plus xn square is equal to 1. So you take a unit vector on n dimensions, and this graph G operates in the following way. It outputs this number, which is 1 by d times the sum of xi minus xj whole square, where I and j are connected by an edge. Okay. So this is, so I am defining an operator which is, so it's, this operator corresponds to this graph G. So it takes in vectors and it outputs a number. Okay. So there are some things to notice about this operator. So first of all, it's non-negative, right? Because you are taking the sum of squares of some things, and this will output something which is at least 0. Okay. It's contracting, meaning you can check that this number will be smaller than 1, which is the length of the original vector. So one way to think about this Laplacian operator is it measures smoothness of input across edges. Okay. So you take in, so suppose it's the case that so across all edges xi and xj are the same. Okay. Then this xi minus xj is always going to be 0, and so you get 0 for the whole quantity. Okay. So it measures the difference of this vector x across edges. Okay. And the reason it's called the Laplacian, and for example the reason the earlier notion was called the conductance, is because there are strong parallels between this and circuit theory in electrical engineering. Okay. I'm not really going to describe that correspondence, but it's a very beautiful theory of how you can view graphs as resistor networks. Okay. So maybe some of the things you have done about finding resistances, about finding the total resistance between two particular nodes in a circuit. So all that kind of theory can actually be converted into statements about graphs. Okay? And that is really making a huge difference right now in algorithms viewing graphs as electrical networks, but I am not going to go into it. But this Laplacian arises in a lot of places, in resistor networks and in spring, if you are modeling springs, if you realize this is like the potential function of a spring. Okay. In any case, so just for for now, just think about this graph as some function which takes in n variables and it outputs a number like this, and we'll look at what the properties of this operator are. So one thing we already said. So suppose all the xi's are the same value. So in this case they are 1 by root n, because we want to make sure that this length is 1. So if they are all the same, then the operator g outputs 0, right? Because xi minus xj is always going to be 0. So this quantity, which this vector which makes the output of g 0 is called a first eigenvector of g. So if you are not familiar with linear algebra, you don't have to wonder about what the meaning of first eigenvector is. So in this context, first eigenvector just means a collection of, so a vector x1 through xn which makes the value of g equal to 0. Okay. One thing is that there may be many different first eigenvectors. So the first eigenvector is not unique. So suppose you have this case where the graph consists of two disconnected parts. Then you realize that this is also a first eigenvector. So suppose you have 2n nodes in the graph and x1 through xn are all equal to each other, whereas xn plus 1 through x2n are all equal to 0. Okay. In this case also this operator g would give 0, because what the operator g does is it takes differences of the value of x across edges. Right. So it does xi minus xj square for I and j which are connected by an edge. So it never looks at I here and j here. So it always looks at things which are connected by an edge. Okay. So here they are all equal. So xi minus xj would always give 0, and here they are all 0 anyway. So they would give 0. Okay. So this is also a first eigenvector, because this also gives 0. So there can be multiple first eigenvectors. So the eigenvector is just a vector which makes g output 0. But anyway, what we'll do is we'll just fix some first eigenvector x. So you can always take the vector which is all equal to be the first eigenvector. Okay. Now the second eigenvector, and I will soon come to the connection between this and finding cuts in a graph. Okay. So just be here for a minute when I will describe this first and second eigenvector, and we'll next see how it connects to cuts in a graph. So the second eigenvector is a vector y that minimizes g of y while being orthogonal to the first eigenvector. So orthogonal just means that the dot product between y and x should be 0. Okay. You all know the dot product, right? So it's just so y dot x, so the dot product or inner product is just yi xi for I equal to 1 to n. So geometrically this corresponds to two vectors who are perpendicular to each other. Okay. So you want to find a vector that minimizes g of y while being orthogonal to the first eigenvector. Okay. And this value g of y, the minimum value of y which is orthogonal to the first eigenvector, is called lambda. It's called the second eigenvalue or the Fiedler value. Okay. So in honor of Miroslav Fiedler, who first introduced this number in this context. Good. So let's see what it does. So one thing is that both this y and lambda, so finding the minimum y, finding the y that minimizes g of y, as well as finding the value of g at y, both of these are can be approximated efficiently. I say approximated because it may be that lambda is not a rational number, so you cannot find it exactly. You have to find some approximation of it. but anyway you can do it efficiently using standard techniques in linear algebra. So I am not going to go into this here, but suppose we know what y and lambda are. So again, so y is perpendicular to x and it minimizes 1 by d sum over I connected to j of yi minus yj square. Okay. So let us just think about what this means. So suppose you have found y, suppose you have found this y. Okay. So what does it mean? So let us view the graph in this order. So suppose y1 is less than equal to y2 less than equal to y3 and so on less than equal to yn. Okay. I mean I have just reordered the order of the, I have just reordered the numbering on the vertices to make sure that this is true. Okay. And now let us say I view the nodes in that order. So this is node 1, node 2, node 3, node 4 and so on, and it's and let us say it's at position y1, y2, y3, y4 and so on until y. Okay. Now the thing is that the intuition is that you cannot have very long edges in the when you are writing the graph in this order. Why? Because if you have a very long edge, say from this node to the first node to the last node, what happens is that this quantity becomes very large, right? So suppose y1, suppose 1 and n are connected and y1 minus yn would be very large, so then that makes this value very large, right? While we are trying to minimize this, so this is just some intuition, but you are trying to minimize this quantity. So you don't want very long edges in this graph, because then that would lead to this being, I mean this sum being large, right? Whereas if you made, whereas I mean if say y1 to yn were connected, and if that was the only edge to yn, you could pull yn here, and that would make the value of this sum smaller. So you don't want, so intuitively in this ordering, when you are looking at the nodes in this way, in the ordering which is given by the second eigenvector, you have few long edges and most of the edges are short. Okay. And then so this is called the spectral embedding. So here's a way that you can, given a graph, you can order it on a line so that the number of edges going long distance linearly is going to be very small. Okay. So spectral embedding minimizes the number of long edges, and actually this way of drawing graphs was proposed in 97 by these guys. Okay. So this is some intuition, and the algorithm for finding a two-way partition is just this. Okay. So you do this spectral embedding, meaning you order the nodes in the order that's given to you by the second eigenvector, and then you sweep over them. So you find, so for each of these cuts, so you look at this cut, you find what is the conductance, you look at this cut, you find what is the conductance, you look at this cut. So there are n minus 1 possible ways to partition this, and for each of these partitions you look at which one gives you the minimum conductance. Okay. And that is your answer. So this is the algorithm for the two-way partitioning problem using the spectral approach. So you find the second eigenvector, order the vertices according to the second eigenvector, and then you sweep across them and find the cut in this order which gives you the minimum conductance. Okay. So this was heuristically proposed by 92, and then a formal result was found earlier in some other context, but then it could be applied to this. So the theorem is this. So if G has a cut of conductance phi, okay, so remember we are trying to find a cut of minimum conductance, then the spectral partitioning algorithm finds a cut of conductance at most 2 root phi. Okay. So phi is some number which is smaller than 1. So root phi is something which is bigger than phi. Okay. So instead of finding phi, it finds something which is slightly bigger than phi. Okay. And this is a very practical algorithm, because you can actually you can find this eigenvector, eigenvalue very quickly using standard linear algebra packages, and so you can find this spectral cut. Okay. So theoretically better algorithms are known. This I mean, you can approximate phi up to better approximation. So this 2 root phi is not very good when phi is very small. Okay, so this root phi becomes much larger than phi when phi is very close to 0. So better algorithms are known theoretically, but those algorithms don't work so well in practice because they involve very complicated steps. So you need to, here you are just finding the eigenvalue, which can be done quite efficiently, whereas there you need to solve a convex program which needs which takes more time practically. But spectral partitioning is easy to implement and it admits good heuristics. So what I mean by heuristics is that on top of just spectral cut, you can have other information about the graph. So maybe you know, you actually also know some other way to find the ordering, and you can use that information to speed up the process, things like that. Okay, so this was for the two-way partitioning problem. Okay, actually maybe, yeah. So let's look at some examples of running this algorithm and see what happens. So first let's just look at this trivial example where you have two parts which are completely disconnected from each other. Okay, so then obviously we would want to find this cut, because this is a cut of conductance 0, right? You have no edges cut. So one eigenvector for this graph is, as I said, this vector, which is uniform on the first half and 0 on the rest. So as I said, it makes this 1 by d xi minus xj square 0. Right? So here is a second eigenvector which is 0 on the first half and uniform on the rest. So notice that these two are orthogonal to each other. Why? Because if you take their inner product, meaning that you take, so suppose this is a vector x, this is a vector y, and you do sum of xi, yi, then x1, y1, x2, y2, they are all going to be 0, right? Because in this half, if x1 is non-zero, then y1 is 0. If xi is non-zero, then yi is 0, and here if xi is 0, then if yi is non-zero, then xi is 0. In any case, xi, yi is always going to be 0, right? So this vector and this vector are orthogonal to each other, and this is also clearly the minimum because you can't go below 0, right? So here the second eigenvalue is also 0. Okay, this Fiedler value is also 0. So this is the second eigenvector, and right. So this, what is the spectral algorithm? So you just order the vertices according to the value of the second eigenvector, right? So you would put all the vertices here at 0, okay, and you would put all the vertices here at the same place, this 1 by root n, if you are putting all of these at 1 by root n. So you would put all the vertices here, all the vertices here, and then you would find what is the best cut along this, and here there is just one thing to check. So you just check this and see the conductance is 0. So here it actually gives the exact answer, right? So I mean, in fact, you have this theorem that this Fiedler value lambda is 0 if and only if the graph is disconnected. Okay. So now, okay, so this basically finishes our discussion of the two-way partitioning problem. So let's look at the higher order partitioning problem. So let's say we have the k-way partitioning problem. We are trying to disconnect the graph. We are trying to find k cuts in the graph. I mean k parts of the graph, so that the conductances of each of the cuts is as small as possible. Okay. So this is a natural generalization of the two-way partitioning problem. So you first find a partition of G into G1 and G2 using the spectral partitioning. So this is a two-way partitioning. Then you see which of them has the smaller eigenvalue. Okay, whichever is smaller, you recurse on that, and you keep going. Okay, and you stop when you have found when you have done this k minus 1 time, so you have k different components. Okay, so the reason why we are looking at this is because, so this lambda value is, so this theorem actually tells us, this theorem actually tells you, I mean if you look at the details of this here, it actually tells you that the second eigenvalue, the smaller the second eigenvalue is, the better the cut. Okay, so So you want to find wait, sorry. Right. So you want to find these. I mean, so you want to recurse on the. No, sorry. I said the opposite. So the higher the second eigenvalue is, the better the cut. So you want to recurse on the side of the. Cut which has the higher cut, which still has high conductance. Okay, so this produces a provably good k-way partition, and this is some very recent work, actually only from 2011, which analyzes this particular algorithm. So this type of work is, so I gave a class here last semester which is on spectral partition, on spectral graph theory, and we covered the proof of this theory. Okay? So all of this is accessible if you know a little bit of linear algebra. And but this was done very recently. So for example, this is an example of research which is being done right now. So analyzing algorithms for partitioning graphs using linear algebra. But the problem is that this type of k-way partitioning is not very interesting on practical instances, as the output may not be a clustering. So remember, we had this differentiation between clustering and partitioning. So in clustering, we also wanted the groups themselves to be individually very well connected. Okay, so the internal conductance to be large, and here we didn't make sure of that. Okay. But the reason why actually these people looked at this partitioning problem is for a different reason. So it turns out that this notion of k-way partitioning is also important in complexity theory. Okay, so the complexity theory is where you are trying to understand which problems are easy and which problems are hard. Okay, and this somehow very recently it has turned out that this notion of partitioning into multiple parts and looking at the conductance on each of the parts. So this has very tight connections to complexity of approximation algorithms in general. Okay, so they looked at the problem for a different reason, but anyway you can interpret their analysis as an analysis of this algorithm. Right. Okay. But now let's go on and look at what algorithms there can be for actually finding clusterings, where you want to make sure that the parts themselves are well connected. So there's a very natural generalization of this. So this is called the spectral clustering approach. So instead of just looking at the second eigenvalue, you look at higher order eigenvalues. Okay? So these higher order eigenvalues are defined as follows. So as always, we take x1 to be the first eigenvector. So this is just some eigenvector which makes the value of g equal to 0. Okay? Now xi is taken to be a vector that minimizes g of xi, conditioned on having xi be perpendicular to x1 through xi minus 1. So earlier we were just looking at the second eigenvector, so I was just 2 and we wanted the second eigenvector to be perpendicular to the first eigenvector. Okay? So but generally you can define all these vectors, each of which are perpendicular to the previous ones, and they minimize g in that subspace which is perpendicular to the space spanned by the previous ones. Okay? And lambda I is defined to be g of xi. So let's look at an example. So here, so again here you have 5 disconnected parts. Okay? So the graph just consists of 5 disconnected parts. So x1 is the vector which is uniform on the first part and 0 on the rest. So this is a first eigenvector, right? Because g of x1 is equal to 0. So because you are just looking at edges across, you are looking at the difference of x's across edges. So now we will take x2 to be 0 on everything except for the second component where it is uniform. Okay. So notice that, right, so the x1 and x2 are orthogonal again because of the reason that we said. If you are taking the inner product, it's always going to be 0, okay, and so on. So the key thing to understand is that we don't have this partitioning beforehand. Our goal is to find the partitioning. But what I am telling you is that these eigenvectors somehow indicate to you the partitioning. Okay? So the eigenvector is defined through a purely linear algebra process. You are trying to find the minimum of this quantity g of x. Okay? but somehow it indicates, so these are the 5 eigenvectors, and it indicates to you which would be the component. So x1 is the set of vectors, set of vertices which are 1 in the first eigenvector. Here the second component is those which are non-zero in the second eigenvector, and so on. Okay. So this is a spectral embedding approach. So you find,
So,
yeah,
does x need to be orthogonal
with all the previous ones. Okay. Yeah. So the eigenvector x1 through xk give an embedding of the n vertices into R to the k. Okay. The way it's done is you take a vertex, you look at the value of that vertex according to x1, okay, according to x2 and according to xk. So for example, here if you look at vertex 1, it would be mapped to 1. It would be mapped to 1 by root n 0 0 0 0. You take the value of the first vertex according to the first eigenvector. Here it would be something like 1 by root n, and here it would be 0. So any vertex in this second group would have would be embedded into 0, 1 by root n 0 0 0, and so on. Okay. So each vertex is mapped to a particular 5-dimensional vector, which is the values for each of the 5 eigenvectors on that vertex. Okay. And this spectral embedding is you look at, so now you view the graph as points in 5-dimensional space, okay, and you find a clustering in that space. Okay. So it seems that we have converted into one clustering problem into another clustering problem, but the thing is that now you are looking at something which are embedded geometrically in R to the 5. Okay. So this is some particular space. Earlier we were looking at graphs in which, it's not clear how, there is no geometry there. But here so suppose for example k was equal to 2. So here you have points in R2, which is just the Euclidean plane, and there we have algorithms for doing clustering. So for example, what you could do is you could look at each of these points and find their median. Okay. So so this is called the k median problem. So you find you find points so that the distances between, the distances from the other points to that point is minimized. Okay. So you have these clustering algorithms like k means and k center and k median, which work in actual geometric space. So in R to the k, for any Euclidean space these work, and then you could. So the idea is you first embed the graph into this geometric space, and then you employ these geometric clustering algorithms. So the way this works is, even though say your points, so these algorithms work only when the clusters are convex. So if you have two clusters which are intertwined within each other, so you have one concentric circle and another concentric circle, then these clustering algorithms don't work if you are just present, if you just give them that. Okay. But on the other hand, if you first do this spectral embedding, then it turns out that these clusters become convex clusters in Euclidean space, and then you can run these standard clustering algorithms there. So these kinds of clustering algorithms are now, were used in some influential papers in machine learning in 2002. And only recently, so these empirical results are very appealing. So the algorithm, as I said, doesn't make any assumption on the form of the cluster. So unlike the geometric clustering algorithms, you don't need to assume that the clusters look a particular way. Okay. And so earlier there weren't too many theoretical results justifying why the spectral embedding algorithm works. But recently, so in 2013, and this is just about a month old, Tamal, De, Rossi and Sidiropoulos, they showed that, so they show proofs that the spectral embedding algorithm actually works in some formal way. So challenges ahead. So we would like to get better understanding of spectral clustering. As I said, so these are some very recent results, and still they don't fully explain why the algorithm works so well. Secondly, everything that I have talked to you is about undirected graphs. Okay? But it's often useful to look at directed graphs. So for example, if you look at the link graph of the internet, which page links to which page, this is obviously a directed graph, right? So just because one page links to the other doesn't mean that the reverse link also happens. Okay? And you would also run algorithms on these kinds of graphs. So for example, PageRank, which is one of the algorithms which drives Google, there you are essentially finding the first eigenvector, you are finding the stationary distribution of this graph. So the stationary distribution means that if you are taking a random walk on the link graph, what is the distribution that you end up in? Okay, and so PageRank, so approximates that distribution. There is more into it, but essentially you are looking at the stationary distribution of the link graph. So it's an interesting question to ask whether there are analogs, and the stationary distribution corresponds to the first eigenvector for undirected graphs. So it's interesting to ask whether there are analogs of the second eigenvector, third eigenvector, and so forth for directed graphs, and whether they can be used to produce better clustering algorithms for directed graphs. So nothing like that is known. Another interesting question is for hypergraphs. So what is a hypergraph? So graphs, as you know, have edges between pairs of vertices. So hypergraphs have edges between maybe not pairs of vertices but triples of vertices, or maybe sets of 4 of vertices. Okay, so a k uniform hypergraph is where you have an edge which connects k vertices into one edge. Okay, so this is also useful where, here we have similarity metric between pairs of edges, but sometimes in some settings you don't have pairwise relations, but if you have relations between groups. Okay, and there also we don't have any good understanding of what is the spectral theory for these hypergraphs. So this is also an important question. And the other thing that I want to mention is that currently there is no principled way to combine the spectral method with other information about the data set. For example, earlier I told you that this graph, that you could have weighted graphs where the weights could be generated according to some metric. So for example, the weights could be the distance between the points, according to some notion of distance. Okay? And can you use that information that the weights are generated in some particular way to find better clusterings? And as far as I know, this kind of thing has not been. Okay, so I'll finish here.
No. So we'll thank the speaker. And have a break till 11:30.